All right. So, okay. In fact, you know what? Since a lot of this is basic information, we'll make this more of a discussion. Okay. So, like we'll make the revision a bit of a discussion. So, it will be more interactive that way. Okay. So, I believe you already know what is momentum, right? You know, momentum is the product of mass and velocity. The When we talk about momentum, the unit of momentum, Ashwish, you remember what was the unit of momentum?
kg meters per second.
Yes.
Yeah, that's it.
Yes, exactly. Yeah, that is it. It's kg meter divided by a second square. All right. Then when we talk about momentum, so we
Are you
know
sure
the,
it's second squared
no, it's not
or is
seconds.
second?
No, it's not second squared. It's meters per second. Okay, and when we talk about momentum, so we know the principle of conservation of momentum, right? The principle states what? Can you go over it?
That the momentum before the collision is equal to the momentum after the collision in a
Yes,
closed system.
exactly, in a closed and isolated system. Now, we had also gone over inelastic and elastic collisions. Had I done that with you? Had I gone over elastic and inelastic collisions with you?
Yeah, but like I prefer to go over it
I,
again. You
yes,
don't
I
really
will
touch
actually.
AS.
Yes, I will go over them with you. Okay. So when we talk about an elastic collision, right? An elastic collision is a collision in which momentum and kinetic energy are conserved. All right. So any collision in which momentum is an obvious principle, right? That momentum is going to be conserved as long as it's an isolated system, as long as there are no external forces involved. The momentum is going to be conserved. The question is whether kinetic energy gets conserved or not. That's the main question, right? So in an elastic collision, momentum and kinetic energy both are conserved. What does that mean? That means that if you calculate the total kinetic energy before a collision, it should be equal to the total kinetic energy after a collision. And that is how we used to solve questions based on it. We used to calculate the kinetic energy before the collision was happening and after the collision was happening. If the kinetic energy would come out exactly the same, we would know that this is a perfectly elastic collision. An inelastic collision, on the other hand, is a collision in which momentum is conserved, but kinetic energy is not. And between you and me, this inelastic collisions are the collisions that we actually see in our daily lives, right? Basically because there's forces like friction involved. So a lot of times when two objects will collide, they might stop moving altogether. So hence, those are inelastic collisions. Elastic collisions do happen, but they are we don't observe them in common everyday scenario, right? Elastic collisions mean that energy is being conserved, which obviously means that there is no energy being used to overcome frictional forces. An elastic collision, hence, an elastic collision is something that we might see when we talk about subatomic particles. In this year, you're going to be dealing with the topic of particle physics. And in particle physics, we are going to study about particle accelerators. And you might have actually already heard about them previously, I'm sure. So a particle accelerator takes two particles, accelerates them to near the speed of light, and collides them with each other to break them apart so we can study their internal structure, or we can study the particles that are inside it. So in those situations, yes, and it can possibly be an elastic collision. But if we talk about, for example, on a snooker table, then that collision is more likely to be an inelastic collision, because some of the energy is obviously going to be used up in overcoming the frictional forces. So in an inelastic collision, obviously kinetic energy before and after is not going to be equal. Now, other than this, there is one other way of figuring out if a collision is elastic or if the collision is inelastic. So this is one way. I will always advise you to use kinetic energy to figure out if the collision is elastic or not. But if you another way of doing it is by using the speed of approach. Let me just write on the formula once again. So in an elastic collision, if we talk about the speed of the particles, or we talk about the speed of whatever object we are considering. Okay, so we have, where's the U1 plus V1 is equals to V2 plus U2, right? If I sum up the initial velocity and the final velocity of particle number one or object number one, and the initial velocity and the final velocity of particle number two, this should come out equal to each other in a perfectly elastic collision. If the equation is inelastic, these values will not come out accurately. These values are not going to come out accurately. You're not going to get the same answer. When you open your textbook, you might see the formula written like this or like this. It's the same thing. U1 minus U2 is equals to V2 minus V1.
So
So
why wouldn't you recommend using this one?
uh, it's not that I don't recommend it. It's just that because with velocity, the direction is really important, right? So in my experience, if you like, sometimes the students do not pay attention to the direction, so they don't properly add the plus or minus sign. That changes the answer. In the kinetic energy formula, the velocity gets squared. So even if the velocity is in the opposite direction, it's negative, it has no overall impact on the answer. That's why I normally tell students to stick to calculating the kinetic energy. This formula is perfectly fine if this is what you want to use, but you just need to be very careful in this case that you need to identify the correct direction of the velocity so you can associate the correct sign with it, right? If, for example, if you look at the formula, if my object is traveling was first traveling towards the right, and after collision it's traveling towards the left, right? So that means my U2 is going, sorry, my V1 is going to become negative, right? Final velocity of object one is going to become minus because now it's traveling in the opposite direction. So instead of subtracting, we will have to add. That's the only problem with this formula, that you just need to be careful about correctly checking the direction of velocities. But if you're proficient with that, if you're good with that, this formula is perfectly acceptable to use. The only reason I was recommending the kinetic energy formula is because by squaring it, we remove any mistakes. Even if you don't identify that the object is traveling in the opposite direction, the value is going to be squared anyway, so ultimately answer will be the same. That was the only reason. Otherwise, both formulas are perfectly acceptable and you can use whichever formula you prefer. All right, so this is you have elastic collisions and you have inelastic collisions. So this is the difference between the two of them, and this is how you're going to identify whether a collision is elastic or whether a collision is inelastic. Now, one thing that you will find when you're solving a past paper questions, right? So you're going to see this year, they often take the topic of momentum and they mix it up with the topic of particles. Because this year, obviously, you're dealing with particle physics. And like I said, particle physics is one of the situations where we can actually see elastic collisions happening. Like it's possible to see elastic collisions happening. So when you're talking about particle physics, right, or momentum related to your subatomic particles, there is a certain formula that you can use. Let me go over that formula with you. This formula, first of all, I'll just go over the derivation with you. The derivation is easy to understand. I don't anticipate you having any difficulty. We know that kinetic energy is equals to half mv squared. And we know that velocity, or when we talk about momentum, momentum is equals to mv, or velocity is equals to momentum over mass. We can substitute v is equals to momentum over mass in equation number 1, which is the equation for kinetic energy. So you get half m momentum upon mass squared. The rest is algebra. So we will get energy is equals to half m momentum square upon mass square. Mass and mass cancel out. And ultimately, your final answer is going to be momentum square divided by 2m, right? This is the formula that you can use to calculate kinetic energy of subatomic particles. Now, this formula is not specifically just for subatomic particles. You can use this formula overall, but normally we use this formula for subatomic particles. Why is this formula mostly used for subatomic particles? The reason for that is because when you talk about your when the particles, especially when we're dealing with them in particle accelerators, they travel quite fast, right? Which obviously brings velocity or makes the assumption of velocity a bit different, because they tend to travel at quite high speeds, especially in particle accelerators. So this is a formula where we can calculate the kinetic energy without knowing the velocity. If we are not aware of what the velocity of the particles is, or whatever object that you're studying, if you're not aware of their velocity, we can calculate kinetic energy by using their momentum instead, right? And you are going to be seeing questions where you are going to be seeing questions related to this, where particles are obviously going to be colliding with each other. This formula, by the way, is not just for calculating kinetic energy. Scientists also use the concept of momentum to figure out the mass of unknown particles. So this entire thing that we are studying related to particle physics. So in particle physics, scientists don't just use kinetic energy and the concept of momentum to calculate speeds or stuff like that. They often also use it to find the mass of unknown particles. So for example, if we go over a practice scenario, okay, we can do a practice scenario. Let's say that we have got two particles, all right? You have just discovered an unknown subatomic particle that we do not have any scientific knowledge of. You and me, we're working together on our collider, on our accelerator, and our goal is to figure out what exactly this particle is. And one of the ways that we can do that is, of course, by figuring out its mass, because like, protons have a certain mass, electrons have a certain mass, neutrons have a certain mass. When you'll do your particle physics, you'll study about a whole different categories and different types of fundamental particles. And you will see one of the defining features is the mass that they possess. So if we take a scenario, let's say that we have an unknown particle. We want to figure out exactly what is the mass of that unknown particle. So we can use a collider. Inside a collider, let's say that we are using a known particle because one is unknown. We don't know the mystery particle. So we want a known particle. The known particle, let's say we decide to go with a neutron. Okay. So we are doing a collision where we have, the smaller particle is unknown and the larger particle is the neutron that I am using for my collision. Both the particles are going to collide with each other head on, like so. Now, after the collision, the particles will separate and they are traveling in opposite directions. Like so. Now, when we talk about the initial velocity, this is before the collision. Now, if I talk about the initial velocity is, let's say, of the unknown particle, the initial velocity is 3 into 10 raised to the power of 7 meters per second. As you can see, like I told you, when we're working with particles, we usually accelerate them to really, really, really high speeds, which is what complicates things up. But that high speed is necessary because only then we will provide enough momentum and enough energy to split the particle apart into smaller particles. And this is exactly how we discovered about protons, neutrons. Actually, not how we discovered it. We knew about protons from the gold leaf experiment. But this is how we figured out that protons are also made up of smaller particles, neutrons are made up of smaller particles, and so on and so forth. And for the neutron, let's say that the initial speed of the neutron is 0. Let's make it stationary. Let's not give it any speed at all. After the collision, the final velocity of my unknown particle is, let's say, 1.09 into 10 raised to the power of 3 meters per second. And for my neutron, 3.4 into 10 raised to the power of 6 meters per second. Our goal is to find out the mass of the unknown particle, right? So, how are we going to do this? We can do this by taking a look at the principle of conservation of momentum. When we are going over the principle of conservation of momentum, so okay, let's solve this together. We're going to solve this together. You're going to go on, along with me. So first thing is first, we should figure out what is the momentum before collision. So can you please go over it with me? What should be the momentum in this case before collision?
It should be for the unknown particle.
For the unknown particle, right? We don't have to worry about the neutron. Why don't we have to worry about the neutron?
Because it's 0.
It's 0, exactly. It's stationary. So obviously its momentum is going to be 0. So we don't know what is the mass of the unknown particle. We know that the speed is going to be 3 into 10 raised to the power of 7. So the momentum before the collision is going to be 3 into 10 raised to the power of 7 m. Now, let's go on to momentum after the collision. The mass of a neutron is known. That is something that we already know quite well. This is the mass of a neutron. This is usually either mentioned in questions or it's going to be given to you with the like in the exam paper where you have your formulas listed and you have the constants and any values that you require listed. So the mass of neutron, electron, these things are usually mentioned over there. Otherwise, they are also mentioned in the question. So we know the mass of neutron is something that is unknown. So now we need to determine what is going to be the momentum after the collision. So can you please tell me how we should determine the momentum after collision?
Give me 1 second. I'm just switching devices.
Oh yeah, no problem.
Okay, can you hear me now?
Yeah, I can.
Okay, so to find the momentum after the collision, you have to times the final velocity of the neutron particle times it by its mass.
Right, exactly. So if we do that, we don't know the mass of the mystery particle, but we know that the speed of mystery particle is 1.09 into 10 raised to the power of 3. Then mass of the neutron is, like I told you, 1.67 into 10 raised to the power of negative 27. And this needs to be multiplied by the final speed, which is 3.4 into 10 raised to the power of 6. I have missed out an important step over here in writing my calculations. Can you pick out where I've gone wrong? Can you pick out? Like, can you see where I have made a mistake in the calculations I've just written down on the screen. Can you identify where I've gone wrong? What mistake I've made? What did I miss?
Taking a look. I think it's to do with the direction, like negative.
Yes, absolutely. Since
So
the
I think
mystery
the
particle is
mystery
now,
particle is supposed to be negative.
yes. So this should have been minus 1.09, right? Over here. Minus 1.09 tends to the power of 3. So now if we know momentum before the collision has to be equal to momentum after the collision, the rest of it is mathematics, which I'm sure you will not have any problem whatsoever. One point six seven into 10 raised to the power of negative 27 multiplied by 3.4 into 10 raised to the power of 6.
So around 5.68 times 10 to the power minus 21.
Yes, absolutely. And then obviously we are going to go ahead and quickly solve for m.
So it'll be 4.09.
Is that the value you're getting for m? To the power of 7
So the answer is going to be
plus
like 1.4 times 10 to the power minus 28 kg.
1.4 or 1.8. I'm getting my
I'll
final value is 1.89 into 10 raised to the power of negative 28.
I'll double check. Yeah, 1.89 times 10 to the power minus 28.
Perfect. Great. Now, right now we haven't done particle physics, right? But there are some practice questions that you're going to find where they're going to ask you to do the calculations. They'll ask you to find the mass of the particle, and then they'll ask you to identify what the particle is. So obviously you will not be able to identify it yet, but when you go over the topic of particle physics, that's pretty easy. But the main thing is that this is how you are going to be able to calculate the mass. So this is one of the applications of momentum that you're going to be dealing with this year, where you're going to say that momentum is going to be, um, uh, 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 you know, um, momentum is going to come quite often mixed up with the topic of particle physics. Not only that, when you now over here, I told you the formula for calculating the kinetic energy of the particle, right? This is the formula that you can use. So you would apply this formula first for the mystery particle, right? We have calculated the mass, so that will not be any problem for you whatsoever. We are going to use the mass of the mystery particle and find the kinetic energy of the mystery particle. Obviously, the neutron itself is not going to have any um, kinetic energy because it's stationary. After the collision, again, you're going to calculate kinetic energy of mystery particle as well as the neutron, because you are well aware of what their momentums are. We have already calculated. So you can use this to find the kinetic energy before the collision, kinetic energy after the collision. If the kinetic energy before and after the collision is coming equal to each other, you will know that the collision is elastic. Go ahead, give that a try for me. Try for me. You can use this formula if you prefer. And since we have also been provided with velocity, so you can directly use the formula of kinetic energy. But try for me and calculate the kinetic energy before the collision and kinetic energy after the collision. And do you think this collision is elastic or inelastic? I will scroll a bit up so you can not only see this is the mass of the unknown particle, mass of the neutron, and of course you have your velocities as well. And I probably have told this to you before as well, but just in case I've never mentioned it, whenever dealing with exponents, try to put the values in bracket just to ensure accurate calculations.
I found that the collision was not elastic.
Yes, absolutely correct. And can you tell me the values, if possible, if you've written them
Yeah,
down, what were you getting before and after?
I got the kinetic energy before the collision was 8.5 times 10 to the power minus 14 joules.
Yes,
And then
correct.
after the collision was 9.65 times 10 to the power minus 15 joules.
Yes, absolutely correct. And if you decide to use this formula, you will get exactly the same answer, right? You will see that the collision is inelastic. So if you do u1 minus u2, you will get 3 into 10 is to the power of 7. And then you will do v2 minus v1. v2 is going to be 3.4 into 10 is to the power of 6. v1 is going to be minus 1.09 into 10 is to the power of 3. So minus minus will become plus. This, I believe, you'll get somewhere around similar to 3.4 into 10 is to the power of 6 approximately. And obviously over here, it's going to be 3 into 10 is to the power of 7. So your values are not coming equal to each other. So that is another way that you can determine that the collision is inelastic. Perfect. Okay. Now, if you remember, there was another concept that we had studied last year, and that was impulse. Do you remember what impulse was?
Impulse equal to change in momentum.
Yes, impulse is basically equal to change in
So
momentum.
mv minus mu.
Yes, exactly. And if you remember, we had studied that your force is equal to rate of change of momentum. And this was the basic principle of Newton's second law.
So change of
So
momentum divided by time.
yes, exactly. Change of momentum divided by time. That was the principle of Newton's second law. And by further solving the equation, we get F is equals to ma, which is what we believe is the what Newton's second law is all about. But it starts actually from force is equal to rate of change of momentum, and then can be further derived to F is equals to ma. Now, this is fine. Let me go over with you the actual portion of the topic that you're going to encounter very, very commonly now in your past paper questions, and then you need to practice solving. And that is momentum in two directions. Okay. When we talk about momentum in two directions, what does that actually mean? That actually means is that so far, like I told you, we have been studying with collisions that are head on. Both the objects are at either horizontally colliding with each other, or both the collisions are happening in such a way that they are vertically colliding. Now, in momentum in two dimensions, you're going to be dealing with objects that are traveling at different directions. So instead of both of them being horizontal or both of them being vertical, they're both going to be colliding with each other at different directions. I'm going to go
So
over.
angular
Yeah.
momentum then. So it's
Sorry.
angular momentum. So it's angular
Yes.
momentum. So it's
No,
like
okay,
different angles.
not exactly angular momentum. Angular momentum is a term we generally use when we're dealing with objects in traveling in a circle. That's our next topic, circular motion. So angular is generally a term we limit to objects traveling in a circular direction. Angular frequency, angular velocity. So the term angular generally does not mean at an angle. It generally means in a circle in physics. So hence I was saying that momentum in two dimensions, meaning that the objects are both colliding with each other in different planes. They are not in the same plane. They are in two different planes to each other. Okay, let me go over an example. I'll go over an example question with you over here. And then I'll also practice one past paper question with you, hopefully, regarding how to solve these questions. And so again, it's not necessary, Ashwish, that they have to be at an angle. Okay. For example, let's say we have an asteroid. Okay. This asteroid is traveling in a horizontal direction. Okay. Now, this is an example, if I'm remembering correctly, I think it's given in your textbook as well. If I'm remembering correctly, in one of the textbooks, this example was given. what the example was that they your NASA had a mission going on at one point, early 2000s, where they were trying to crash a spacecraft into a comet, right? And their purpose was they were trying to actually study the composition of the comet. Now, what actually happened was that while this mission was going on, they discovered that there was an asteroid that was heading towards our planet. There was a small chance of collision, right? They were worried that it might possibly collide. So what did they do was they sent a spacecraft towards the asteroid, crashed that spacecraft into the asteroid, and as a result deviated its direction and changed its direction out of the Earth's path. So the example that was that can we hit an asteroid hard enough to deviate it from its path, because that's when before they did the mission, that's what they were calculating, that if we send the spacecraft over there at a certain speed, at what speed is it actually going to successfully deviate the asteroid from its path. So let's so in that situation, let's say we have an asteroid, okay? That asteroid is traveling at an initial speed of, let's say 12.6 kilometers per second. Now, we have a spacecraft. This spacecraft is not traveling horizontally. To make it easy, let's consider that the spaceship is traveling vertically. And the velocity of the spaceship is 6 kilometers per second. So again, you can see that these are horizontal and vertical, right? So hence we say they are not at angles technically. It's not like they are traveling at 10 degrees to the horizontal or 20 degrees to the horizontal. They're completely horizontal and vertical. But since they are in completely opposite directions to each other, so this is also considered as momentum in two directions or momentum in two dimensions. So uh, okay, so this is before the collision, right? Now, after the collision, what the scientists are expecting is that after the collision, the asteroid is going to deviate. Asteroid is going to deviate from its path, and as it is going to deviate from its path, the spacecraft will stick to the asteroid. The spacecraft is going to stick to the asteroid, and the asteroid, which was initially traveling in a horizontal direction, would then deviate from its pathway. Now, for the scientists to figure out exactly how much deviation they are going to see, is it going to deviate enough that it would be out of impact line with the planet? They needed to determine the angle. And this is where momentum in two directions come in. This is all related to vectors. So as long as you have a good grip on vectors, this is not going to cause you a lot of problem. Now, let's see if we can figure out, if you and I can figure out exactly what is going to happen. We need to know the final velocity, which we are unaware of. And we also are not aware of we're also not aware of what the final collision is. Okay, so there are two types of questions that you're going to see. Just like when we talk about velocity, just like in the topic of kinematics, we would take velocity traveling at an angle and we would divide it into vertical component and horizontal component. Similarly, momentum is also a vector quantity. It can also be divided into a vertical component and into a horizontal component. When you're solving questions related to momentum like this, you have to calculate the momentum in the horizontal direction. How do you do that? By looking at the horizontal component of velocity. If you can figure out the horizontal component of velocity, you can figure out the momentum in the horizontal direction. If you can figure out the vertical component of velocity, you can use mv to find out the momentum in the vertical direction. Once you have calculated the momentum in the horizontal direction and the vertical direction, you can make a vector triangle and calculate the result. That is the basis of it, right? So it's pretty much the same thing that you have already been doing so far. In kinematics, when we were doing the topic of projectile motion, if you wanted to find out in a vertical projectile motion the overall velocity, what did we do? Calculate the vertical component, horizontal component, calculate the resultant. Same thing over here. You can use the vertical component of the velocity to find the vertical component of momentum. Horizontal component of velocity, horizontal component of momentum. And once you have the vertical and horizontal component, you can determine the momentum, resultant momentum of that scenario. So let's start with momentum before the collision. Again, momentum before the collision, I cannot directly do m1 v1 is equals to m1 u1 plus m2 u2. Again, because they are not in a head-on collision, right? They are both colliding in two different directions. So we are going to have to determine before we can go around solving the question, we have to figure out the initial momentum, resultant momentum. So to do that, we are first going to take a look at the momentum in the horizontal direction. Now, lucky for us, before the collision, there are no angles involved. After the collision, we have some angles. But before the collision, they are either completely horizontal or completely vertical. Let's start off with our asteroid. My asteroid has no vertical component because obviously it is completely horizontal. So I will figure out the momentum of the asteroid. Let's say that the mass of the asteroid is, what should I make the mass of the asteroid? 6.1 into 10 raised to the power of 10. Yeah, I think that seems reasonable. Okay. And the speed is obviously 12.6 kilometers per second. You do need to convert this into meters. So we will multiply by 1,000. And this is going to give us momentum of the asteroid. Since the asteroid is traveling in the horizontal direction, so this is my horizontal momentum. So the answer I'm getting, correct me if I'm wrong, but I'm getting 7.69 into 10 to the power of 14. This is going to be my momentum in the horizontal direction. Then we will determine the momentum in the vertical direction. In the vertical direction, I only have the spacecraft, right? There is no vertical component of the asteroid involved. So for the spacecraft, again, let's say that the mass of spacecraft is 4,000 kilograms, actually. 4,000 kilograms. Multiply that by its speed, that is 2.4. No, sorry, what had I written? 6. 6 into 10 raised to the power of 3. 2.4 into 10 raised to the power of 7. Right? Now, what are you going to do is that you are now going to determine the resultant momentum. Okay, how are you going to figure out the resultant momentum? So this is momentum before the collision. Okay, let's make a vector diagram. In a vector diagram, this is my momentum before the collision in the vertical direction. Then this is my momentum before the collision in the vertical direction.
Would you have to add them and then like take the square of both and then add them and then square root it?
Yeah, you can use Pythagoras theorem. You're right. You can use Pythagoras theorem to solve it. This is the hypotenuse is my momentum after the collision, right? My adjacent and my opposite are the momentum before the collision. Both of these are momentum before my collision has happened. This is the momentum that is in the horizontal direction. So if you were given with this over here, we had it completely horizontal, but if it was acting at an angle, then you would resolve the component. Just like in kinematics, you would resolve the horizontal component, and that would be the horizontal. Then you would resolve the vector component, right? Just like in kinematics, you just do it exactly like that. If it's at an angle, resolve the vertical component, horizontal component. I will go over practice questions with you on that, so that's no problem. But the main thing is resolve the vector. So that's the entire concept. Resolve the vectors in the horizontal direction, resolve the vectors in the vertical direction. This is the momentum before the collision. This is also the momentum before the collision, but it's in the vertical direction. The resultant momentum is the momentum after the collision. And this angle theta that I had marked over here with the horizontal, this angle theta. And now we can figure, if now that we have this piece of information, we can find out pretty much every information that we require, right? So we know that momentum before the collision in the horizontal direction is 7.69 into 10 raised to the power of 14. This is going to be 2.4 into 10 raised to the power of 7. Now, you do need to know how to make this vector triangle, because the vector triangles do come quite commonly related to momentum, and they often ask you to draw it to scale. Like, there are quite a few questions where they ask you to make it to scale. So that's something that we have to practice. So let's go ahead and find out what our momentum is going to be. To find the momentum, we are going to find the momentum, we're simply going to apply Pythagoras theorem. You will resolve this exactly like every single vector triangle that you have ever studied. So if you can do the calculations and let me know. Yes, Ashwish?
Why would the resultant be the momentum after the collision?
Because what is happening is that we know momentum before the collision is equal to momentum after the collision, right? Whatever the momentum before the collision is, that is equal to momentum after the collision. Think of it this way. Imagine the momentum is related to force, right? Force is rate of change of momentum. This object is applying a horizontal force. This object is applying a vertical force. So this is the ultimate momentum is the resultant force. So just like imagine if there is a tugboat, okay? You might have gone over this example previously as well. If there is a tugboat and it's being pulled in two directions like so, right? So it's the resultant direction is going to be in the middle. Similar concept over here. Do not think of momentum before as something different, something separate. This is all just one scenario. What is actually happening is that momentum before the collision is related to the force. This is applying a force horizontally. The spacecraft is applying a force vertically. The resultant of those two forces causes the asteroid to deviate. That is how momentum before and momentum after are actually linked to each other. So momentum, what is actually going to happen? Let me just add one thing. Momentum before the collision in the horizontal direction is equal to momentum after the collision in the horizontal direction. Right? Technically, when I'm writing momentum before, I am bypassing a step. Technically, momentum before the collision in the horizontal direction is equal to momentum after the collision in the horizontal direction. Similarly, momentum before the collision in the vertical direction is equal to momentum after the collision in the vertical direction. Hence, we can resolve the two vectors and we can get the resultant afterwards. That is the reason, because before and after are equal to each other. So whatever is the before vertical, the after vertical is the same. Whatever is the before horizontal, after horizontal is the same. So yes, I've written it as before, but we can also write it down as after. It doesn't make a difference because momentum before and after are equal to each other. That's why I can use the before values to calculate the momentum after, the resultant momentum after. Does that answer your question? Is that making
So that's
sense?
basically the total momentum.
Yes, exactly. Yes. So this is basically going to be the total momentum that you're going to see afterwards. And this is the momentum in the horizontal direction, and this is the momentum in the vertical direction. Exactly like you deal with velocity. So if you remember your topic of kinematics, in kinematics, what would happen is this, that you would have your momentum. Sorry, I said momentum, velocity, right? So we would have resultant velocity, and then we would have the horizontal component, and we would have the vertical component. This is exactly the same thing. So the horizontal component and the vertical component before and after the collision will be the same. So hence we can go ahead and determine what the resultant velocity is. The only thing that's different is the angle. The momentum before and after in horizontal and vertical components will be the same. The angle is where it becomes different, hence the resultant is different. That's the basic logic behind it. So in this particular case, what are we going to do? So if you calculate your resultant velocity, you can simply calculate it by using your Pythagoras theorem. So I am getting my answer out as 7.69 into 10 raised to the power of 14 kilograms meters per second. So this is the momentum that is after the collision. Once you've calculated the momentum after the collision, you can also calculate the velocity over here, right? So that you can simply do by using the formula mv. When you are talking about the mass, so please remember that since the asteroid and the spacecraft are sticking with each other, so we will take the total mass. Mass of the spacecraft plus the mass of the asteroid. So 6.1 into 10 to the power of 10 plus 4,000. That's going to be the total mass. And velocity we have to determine. We already have the... One second, sorry. We already have basically our final momentum. So we can go ahead and we can use that concept to figure out the velocity. And obviously, once we have the velocity, we can also go ahead and figure out the angle. The angle is not going to be much of a problem either. So you can use mass into velocity. The mass is going to be 6.1 into 10 to the power of 10 plus 4,000. And momentum we have calculated. So my final velocity is coming 12.6 kilometers per second. And finally, when we talk about our angle theta, so you can simply use tan theta if you want, or sine or cos, whatever you like, and you can calculate the value of theta. So this is how the scientists determine how much the asteroid is going to deviate. And once they determine how much the asteroid is going to deviate, obviously they had information of the path of the asteroid and exactly what route it is following and how much deviation is needed. So they were able to figure out exactly how much the asteroid is going to move and if it is going to move enough out of the way that it would be, out of impact line. So this is how they
How
determined
would
it.
you calculate the angle?
You have your vector triangle, right, over here. You know the adjacent.
Oh, right, yeah, okay.
Yeah. So in the
So
hypotenuse,
let's use
and yeah, you can use
trigonometry.
any trigonometric. Yeah, any trigonometric ratio. So this is how
Yeah, I see.
basically you're going to be solving the questions, right? Now, so what you have to basically is this entire thing is all vectors. Momentum in two directions, the entire topic is all vectors. You just have to remember that whenever you're solving questions related to this, first find the momentum in the horizontal direction, find the momentum in the vertical direction, and then resolve for the resultant. That's exactly the steps that you're going to be following throughout. And the second portion related to this is drawing your vector triangle. I'm going to obviously practice with you how to draw vector triangles, but you should know how to draw your vector triangles, and they usually ask you to draw them to scale. So you're going to have to obviously do all the measurements and everything and draw it accordingly. Okay, all right. Okay, Ashwish, so I think we'll go ahead and we will stop it over here for today. Theoretically, this is all you need to know, but the main and only tricky thing is solving these questions. So from our next class, tomorrow we'll go ahead. I'll go over questions with you on how to actually go about solving questions that we see in our past papers exam. And that is the main thing you have to get a hang of. If you get a hang of how to solve the questions, they all follow the same pattern. So once you have a hang of it, you can solve them pretty easily.
So yeah, makes sense. Thank you.
Okay, all right. Thank you so much, Ashwish. I'll see you in the next class then. Have a good day.